Alright, what drives a reaction to be spontaneous? Basically, there are two different forces at work that drive a reaction to be spontaneous, either enthalpy or entropy. Enthalpy, remember, is the heat content within something, and in general, exothermic reactions were favored. Entropy is the disorder of a system, and in entropy favors things that are more disordered. Think of it like your bedroom. Your bedroom starts off nice and neat after your mom cleans it, or after you clean it, but by the end of the day, in some cases, or by the end of the week, it's a disaster area. Because the universe favors the production of something that is more disordered. So this means that, in general, the universe favors exothermic reactions that are, so with a negative delta H, and disordered, things that bring more disorder, or a increase in entropy, so a positive delta S. In chemistry, this means that the universe favors systems in a less condensed state. So if we're talking about, say, phase change, the universe would favor a system in its solid form far less than it does something in its liquid form, and even less than something in its gas form. Because this is a difference in how condensed it is. In solids, all those molecules are right next to each other. In liquids, they're free to move around, but they're still pretty close. But in gases, they're free-flowing. There's lots of chaos. There's lots of entropy. And aqueous solutions fall somewhere between liquids and gases. And this is because actually some solids, carbonates in particular, will actually bring more order to a system. If we're talking about something as being an element or a compound, the universe actually favors the production of compounds. Because when a compound forms, bonds are made and there's energy that's being released. So the production of compounds is thermodynamically favored. And all of this deals with whether or not a reaction is spontaneous, whether or not a reaction will occur after we've reached activation energy, whether or not a reaction will occur on its own, or if it requires additional energy. And notice how we've made no mention how fast a reaction occurs. That's kinetics. That's the next unit. So we're not going to be talking about speed. We're only talking about whether or not it's a downhill slope. So this whole chapter is about thermodynamics. And thermochemistry dealt mainly with the first law of thermodynamics, that energy can be neither created nor destroyed. It's just shifting. And that was the basis for Hess's law. This unit, or this segment, deals with entropy, which covers the second and third law. The second law is basically entropy itself. The universe is constantly increasing in disorder. Basically, it's that you can never break even. You're always going to have to pay the universe something. The third law of thermodynamics deals with absolute zero, or zero. At absolute zero, or 0 Kelvin, all movement within an atom, even the electrons, stop. They slow down to a halt, and by then, there's no chaos. Everything is in its most condensed phase. When this happens, compounds and elements form perfect crystals. So anything that's a perfect crystal is at 0 Kelvin, and it has no movement, and therefore it has no chaos. So the entropy of any perfect crystal is 0. So, first law, conservation. Second law, everything is going to become more chaotic. And the third law deals with perfect crystals. The third law, however, allows us to calculate the entropy of any system that's higher than 0 Kelvin, which is pretty handy because we will never be at 0 Kelvin. Which will come in pretty handy because if delta G, which stands for free energy, and delta H ever equals 0, and we're asked why is S, why is the entropy not 0, It's because we're not at 0 Kelvin. So it's possible for those two values to be 0, but chaos to not be 0. Now, science isn't perfect. Sometimes we need to go back and state the obvious. For example, in thermodynamics, there's a first law, there's a second law, there's a third law, and later we said there's something so obvious it stared us in the face, we need to go back and make it 0. So there's actually a zeroth law. But I think it's one you'll actually embrace because it's very simple. The zeroth law of thermodynamics is that if A and B are at thermoequilibrium, and B and C are at thermoequilibrium, then that means that A and C are at thermoequilibrium as well. So we can predict the value for delta H, be it positive or negative. It's going to increase if chaos is going to, delta S, if entropy is going to increase or decrease if we just embrace a couple concepts. First off, the greater the disorder, the more randomness in a system, the larger delta S is going to be. So if we go from something that is solid to something that is liquid or something that is gas, we are going to be increasing. So we're going to have a positive delta S, which ties into number 2. It will always be greater. We're going to have massive increases between solid to liquid, and even more massive from liquid to gas. If you take a solid and you dissolve it into a liquid, well, you've broken those molecules apart. They're now free to move around. You've increased the chaos, and so we're going to increase delta S as well then. We have another positive delta S scenario. There's only one exception, remember from before, carbonates are an exception. They will actually bring more order to a system. Anytime a gas is given off, that's an increase in entropy because now you're producing a gas, has a lot more chaos in it itself. Also, generally speaking, the more complex a molecule is, the more chaos is there that's housed within it. And this is all because it has more electrons. Some people oversimplify this and say it's the increasing molar mass causes an increase in chaos. That's only partially true, and people and AP graders have taken points away for that because it's an overgeneralization. An increase in the number of atoms is also an increase in the number of moles, and an increase in the number of electrons, and therefore is an increase in chaos. So just saying molar mass increases and therefore more chaos, that is not necessarily true. It's the increase in the complexity of the molecule. And often, if there's an increase in the number of moles on one side of the reaction or the other, if there's an increase in the number of moles, that's also an increase in chaos, because now you have more in a certain place. And this is in particular, especially when you're talking about gases. In general, the more number of arrangements you can have of things, there's a greater chaos in the system. Be it if you have all the gas on this side or all the gas on that side, or if you have them equally spaced out. There's an increase in the amount of chaos if there's an increase in the number of arrangements possible. So let's say you had solid sugar and you dissolved it into water. You know that sugar dissolves into water. So we're taking a solid and we're making it into an aqueous solution. That's going to be an increase in our chaos. So an increase in delta S. So we would expect to have a positive delta S. Alright, what if we have iodine vapor? Remember, vapor is a gas that is usually a solid or liquid at room temperature. If we have a vapor that condenses and cools into crystals, we're going from a gas down to a solid. Well, that is going from lots of chaos to a little bit of chaos. So we would expect to have, you guessed it, a negative delta S. Here's a question at the AP test and AP multiple choice love to ask, which of the following would have the greatest increase in entropy, greatest increase in chaos? So we have to rank these. Which one would be the most, which one would be the least? So let's look up here. First off, carbon dioxide goes from solid to a gas. It sublimes off. That's a massive increase. We go from being a solid, we skip right over being a liquid, and we're going to being a gas. So if I was going to rank that, I would say that's at least like 3, 4 stars. So I'm going to make that a positive delta S, a big positive delta. Alright, next one I've got hydrogen gas and chlorine gas becomes hydrochloric acid. So hydrochloric acid as a gas, hydrochloric vapor. I have 2 moles of gas on the right, I got 2 moles of gas on the left. Without any tables here, I really couldn't tell you what that's going to be. If I was going to guess, I'd say it's probably going to be a very small change. So this one, I'd say it's kind of a wash. Next, I have a solid that becomes a liquid. So that one, again, is now an increase in chaos, but only a small increase. So I would rank that less than this one. If this was 3, let's make this one 2. Lastly, we have carbon as diamonds becoming carbon as graphite. Well, diamond is that thing on your mom's ring, in case you didn't know, and graphite's what you keep in your pen. Obviously, the diamond in a ring is going to be more ordered than the graphite in your pen, because when you scratch something with a diamond, it doesn't fall apart. But if you take your pencil and run it across the paper, it leaves trace amounts of carbon, and that's what you're seeing. So this must be an increase in entropy as well. However, we're going from a solid to a solid, so this would probably be the least amount on this one besides B. So now we just have to look at what we classified each thing as. Obviously, we can see that A is the greatest increase in chaos, and therefore that would be our answer. Previously, when we were working with enthalpy, we used the Big Mama equation, the equation that's the sum of all the things that gave us the heat of reaction, or the enthalpy of the reaction, which it was the sum of the products minus the sum of the reactants. Well, guess what? We're going to use the same type of formula here, except for now, instead of H, we're going to sub in S for entropy. So if we know the entropy of all of the products, we can sum them up and subtract from them the entropy of the reactants to give us the entropy of the overall reaction. And our units for this are going to be joules per Kelvin mole. If you look in your packets, it looks like it says joules per Kelvin x mole. It's just a typo. But it's joules per Kelvin mole. So let's say we're given a problem like in sample B, where we're asked to find the entropy change, the delta S, for the reaction, and we're given the entropies for each of the reactants and the product. If we plug them into the Big Mama equation, we'll be able to find the entropy change for this reaction. So let's, without further ado, do that. So we plug in our reactants, our products, and we sum up our reactants, and we should get delta S, which once you plug these in, you end up with negative 188 joules per Kelvin mole, which makes sense because you're starting with 3 moles on the right, you're ending with 2 moles on the left. Oh, backwards. Starting with 3 moles on the left and ending with 2 moles on the right. So you're becoming more ordered. So we're decreasing in chaos, decreasing in entropy. And while we're examining things, look, as the complexity of these compounds increased, the entropy also increased. SO3 has a higher entropy than SO2, which has a higher entropy than the simplest of them, oxygen.